Hello everyone, I'm Oeissyah binti Arbain and I will be presenting the first part of our discussion on reservoir rock properties today. Before we begin, I would like to introduce our group members, Muhammad Hafiz bin Muhammad Syukur, our data analyst, who also help prepare our presenting materials, Migel Dandi Raihan, who will be presenting later in this presentation, Abu Hurairah Ashik, our other presenter. We have worked together as a team to bring you this information on reservoir rock properties. Today, we will be focusing on three key areas: capillary pressure, relative permeability, and the Purcell method. Now, let's dive into our topic starting with capillary pressure. Capillary pressure is defined as the difference between the pressure of the non-wetting phase and the wetting phase across the interface of two immiscible fluids. The formula for capillary pressure is PC equal to PNW minus PW, where PC is capillary pressure, PNW is the pressure of the non-wetting phase, and PW is the pressure of the wetting phase. There are three main methods to measure capillary pressure. First, porous plate method. Second, mercury injection capillary pressure, MICP. Third, centrifuge method. Let's look at each of these methods in more detail. Mercury injection capillary pressure, MICP. MICP is based on the principle that mercury, a non-wetting fluid, is injected into a rock sample at progressively increasing pressures. The volume of mercury injected at each pressure increment is recorded. The procedure for MICP is as follows. A rock sample is placed in a chamber and vacuumed. Mercury is injected into the sample. The pressure is gradually increased and the volume of mercury entering the pores is measured. Porous plate method. This method uses a porous ceramic plate that allows water to pass through but not air or oil. The rock sample is saturated with the wetting phase and the non-wetting phase is introduced under controlled pressure. The procedure for the porous plate method is the rock sample is saturated with water. It is then placed in contact with a porous plate. Air or oil is introduced at known pressures. The capillary pressure is measured by the pressure required to displace the wetting phase from the sample into the porous plate. That's all from me, and I will now pass the presentation to my group mate Abu Hurairah Ashik, who will continue with our discussion. Thank you.
Hello, my name is Abu Hurairah Ashik. Now I'm going to talk about capillary pressure determination by the centrifuge method. This method utilizes centrifugal force to create a pressure gradient across the rock sample, leading to the displacement of wetting phase by non-wetting phase. First, the rock sample is fully saturated with water, then it is placed in a centrifuge and spun at various speeds. Then the centrifugal force creates a pressure gradient, and the pressure at different points within the sample is calculated based on its force. And at the end, the volume of the displaced fluid is measured. This method is advantageous because it allows us to study the fluid displacement under controlled conditions, providing valuable data for reservoir characterization and simulation. Next, I am going to talk about relative permeability. Relative permeability is a critical concept in reservoir engineering, representing the ratio of effective permeability of a particular fluid phase to the absolute permeability of the rock. This ratio is crucial for understanding the fluid flow dynamics of different fluids within the reservoir, as it indicates how easily a specific fluid can move through the rock compared to the rock's overall permeability. Finally, let us talk about the Purcell method for determining the relative permeability. Purcell method estimates the relative permeability using capillary pressure data obtained from mercury injection capillary pressure tests. First, we have to calculate the Lagrange J function. Then we have to calculate the effective saturation. Then we will integrate the capillary pressure data, and at the end we will integrate the numerical data. The parcel method is beneficial because it provides a way to estimate relative permeability using non-destructive method, offering valuable insights into the fluid flow characteristics of the rock. In conclusion of my speech, understanding the centrifuge method for capillary pressure determination and concept of relative permeability and parcel method for estimating relative permeability are essential for optimizing reservoir performance. These techniques and definitions are fundamental for effective reservoir management and enhanced oil recovery. At the end, thank you from my side. My next speaker will speak further.
In this slide, I will explain to you the leverage J function step. First of all, we need to select the capillary pressure data by choosing sample 3 at the depth of 2500 meters and collect the capillary pressure and water saturation data for this sample. The second step is converting the capillary pressure to leverage J function using the formula. The formula is JSW, or the dimensionless J function, equals to capillary pressure divided by interfacial tension times cos of the contact angle and times the root of permeability divided by porosity. In the next step, we will calculate for the normalized water saturation using the formula SWN, or the normalized water saturation, equals to water saturation at the given point. Negative irreducible water saturation, the ones that remain immobile, divided by 1. Negative irreducible water saturation, negative the residual oil saturation. Okay, we will continue with the leverage J function step. This time we will calculate the effective saturation by using formula water saturation negative reducible water saturation divided by 1 negative residual oil saturation negative by reducible water saturation. And the next one will be integrating capillary pressure data. So in this step, we will integrate the reciprocal of the square root of capillary pressure to obtain the relative permeability values using these two formulas. And the last one will be numerical integration. So this is the final step where we use numerical methods like trapezoidal rule to integrate the data. So this will be the final data of the leverage J function. In the first row, this is the column represent the average water saturation within the rock sample. In the second row, there is PCI bar. This column shows the capillary pressure in bar. And the third row is reciprocal of the square of the capillary pressure. The next row will be the absolute permeability of the rock. Next one will be effective water permeability. Sixth row will be relative water permeability. The seventh row will be effective oil permeability, and the last row will be relative permeability to non-wetting phase. The last two rows were the one that uses numerical method. For the KABs, it means absolute permeability. The next one is the graph. In this graph, it will inform about the relative permeability curve. It shows the relative permeability from the scale 0 to 1.4 and the water saturation from the scale of 0 until 1.2. And for the KRW, or the relative permeability to water, this curve shows how water's ability to flow changes as water saturation increases. In general, The relative permeability to water increases as water saturation increases. This means that water flows more easily when there's more of it in the pores. For the next one, the red line will be KRNW, the relative permeability to non-wetting phase. This curve shows how oil's ability to flow changes as water saturation increases. In general, the relative permeability to non-wetting phase decreases as water saturation increases. This means that oil flows easily when more water is present. In conclusion, Purcell relative permeability model best fit to the experimental data of the wetting phase relative permeability independent of the fluid system, and the saturation history not a good fit for the non-wetting phase. That's all from our presentation. Thank you.